just to say. Okay, so for the last couple of weeks, we've been talking about equilibria. Last week, we talked about acid-base equilibria. So there's more than just doing regular old acid-base equilibria. Um, you can do other things too, like called buffers. And this is what we're going to be talking about today. We're going to be talking about buffers. That's what the short title is for additional aspects of aqueous equilibria, right? The short title is buffers, right? And uh, let's just talk about what they are real quick. So, hold on one second. Sorry about that. I forgot which button's which. There we go. Okay, so the effect of acetate on acetic acid equilibrium, right? So we remember that acetic acid is the weak acid, right? And when it dissociates, it becomes protons or hydronium ions and the acetate ion, right? So it turns out that sodium acetate, right, is a very strong electrolyte, which is actually funny because acetic acid is a very weak acid, right? It makes kind of sense though because acetic acid is like an organic compound, right? Whereas sodium acetate is a ionic compound, and that's why it's such a strong electrolyte, right? Because things that are strong electrolytes dissolve in water easily, right? Like sodium chloride. So the interesting thing about this is that sodium acetate has the acetate ion, right, when it goes into water. But then also acetic acid, when it goes into water, has the acetate ion. So these two things have a common ion, right? When you add them to water, and that has some implications. That has some implications. And we'll talk about that in just a second because we need to take roll, and we'll take roll by answering this question here. Which of the following best describes sodium acetate? It's a strong electrolyte. It's a weak electrolyte. It's a middle of the road electrolyte. Or it's not an electrolyte at all. All right, so this was the distribution right here. This was the El Distribuciano, right? The answer was in fact A. It's a strong electrolyte. So uh, I will attribute the fact that three people got this wrong because you're vigorously writing your pre-labs today, right? But acetate is definitely a strong, sodium acetate is definitely a strong electrolyte. So, um, switching back now, switching back now. So the presence of acetate from sodium acetate in acetic acid will shift the equilibrium, right? Because remember Le Chatelier's principle, you add in some more products, it'll shift the equilibrium towards the reactants, right? And so here, if you add acetate, because acetate is the conjugate base, and it will be the product, right? The product, it will shift the concentration of the acid, the protons, so that there's less protons. Okay, it will make more of the acetic acid that hasn't been disassociated, and that makes sense too because remember that in this equilibrium process, we get to a point where there's there's a certain concentration of protons and a certain concentration of the conjugate base. And if you add more conjugate base, right, then you make it so that it's not equal anymore. The equilibrium is not there anymore, right? And so it's still trying to get back to equilibrium. And so some of these acetate ions will come over and just gobble up these protons or just one proton at a time, right? And in doing that, it makes it so that there's less protons in solution, right? Making it less acidic and making more of the acetic acid that hasn't been dissociated yet. Just remember that when you add in more of the acetate ion, right, we will get less protons because these acetate ions will gobble up all the protons, making more of the acetic acid that is less soluble, right? That is not a strong acid, okay? So what this is called is the common ion effect, okay? We call that the common ion effect. So the formal definition of the common ion effect is that whenever a weak electrolyte and a strong electrolyte containing the common ion are together in solution, the weak electrolyte ionizes less than it would if it were alone in the solution. Okay, so that that obviously affects acid-base equilibria, right? Because in acid-base equilibria, as we saw in the previous slide, you added some sodium acetate into some acetic acid, and you'll get less protons, right? So you'll get less protons. So here's your next question. Here's your next question. Which of the following is not true about the common ion effect? Remember, it says not true. Okay, not true. And per your request, I checked my grammar on these on these answers. Okay, it involves a weak electrolyte and a strong electrolyte containing a common ion. That sounds reasonable, I think. A weak electrolyte ionizes more than it would if it were alone. It affects acid-base equilibria, where all of these are true. All right, so the distribution, sorry, the distribution here is this, and the vast majority of you got that correct. The answer is in fact B, right? Exactly. See, I knew somebody was paying attention, even though she's vigorously writing her pre-lab. She's paying attention, right? Anyway, so here's an acid-base example then, right? If I were to have a pH of a solution, oh, sorry, what is the pH of a solution, right? That's made by adding 0.3 moles of acetic acid and 0.3 moles of sodium acetate to enough water to make a 1 liter solution, right? So again, we have our acetic acid right here, okay? And then we have our protons there, or H3O, hydronium ions right there. And then we have our acetate, okay? And remember that the Ka equals the products, which in this case are the protons and the acetate ion, divided by the concentration of the acetic acid itself. And we already know from a chart that the Ka of acetic acid is 1.8 times 10 to the negative 5, right? So all that stuff you already know. So here's the new stuff right here, okay? Since we have a common ion now, right? Instead of the ice table being 0.3, 0, and 0, what do we have now that's different? It's going to have 0.3 here as well for the acetate ion, right? And the reason why it has 0.3 on the acetate ion is because remember that the problem here says that not only do you have a solution of 30 moles of sodium acetate, you also have a solution of 30 moles, 0.3 moles rather, of acetic acid. So you have to take into account the 0.3 moles of the acetic acid as the initial, and you've got to take into account the 0.3 moles of sodium acetate in the initial. Okay. So that changes then our equilibrium equation just a little bit, right? We still have the same change. It's going to be minus x plus x plus x, right? The equilibrium equation for the acetic acid will be the same, 0.3 minus x. The protons stay the same too, so it's just x. But now on the acetate ion side right here, right, it's going to be 0.3 plus x, okay? 0.3 plus x. So that's the difference in the ice table now. That is the difference in the ice table now, okay? So continuing in this example, right? Continuing this example, we have all this stuff happening here, right? Where we have the Ka, right? And then from the ice table, X is the hydronium ion or the proton concentration, right? And then the 0.3 plus X is the concentration of the acetate ion, right? And then that's all divided by the acetic acid, which is 0.3 minus X from the ice table. And once again, this is a you're welcome moment, right? Since we're doing acid-base equilibria for a weak acid, it's so weak that the change in X for a plus or minus, right, is so low that we can just drop the X, right? So I think that Ms. Dickens said that in discussion yesterday, and then she came to me and asked me what that meant or something. But yes, if you're doing chemical equilibria, which is the chapter we did before this one, then you have to do the quadratic equation. But if you're doing acid-base equilibria, you can just drop the x. That way you don't have to use the quadratic equation, right? So all that leaves you with, you see how over here we have the Ka, and then the 0.3 here, the plus x is gone, and then over here the minus x is gone. So that just gives you x times 0.3 divided by 0.3. right? And then x then equals 1.8 times 10 to the negative 5. Why? Because these numbers cancel out, right? Those numbers cancel out. The 0.3 cancels out. Again, you're welcome. I know you're not really seeing that yet, but you're welcome anyway. Okay? Because look, there's like no math to do at all because they cancel, right? So they cancel. And so literally x is just the Ka now. And that means then x, the Ka is the hydronium ion concentration now, right? And then for you to be able to get the pH, all you have to do is take the negative log of the hydronium ion concentration or the proton concentration, and you get it to be about 4.74 as pH. Okay? So in this particular example, right? In this particular example, those numbers did cancel out because the 0.3 was the same for both the initial of the starting acetic acid and the acetate ion, but it could be different next time, and you won't have these numbers be the same, and they won't just cancel out. You might actually have to do some rudimentary math, like multiply both sides by the bottom number and then divide, that kind of thing, right? Or do a cross multiplication, whatever. By the way, that's the same thing as cross multiplication. Doing multiplying by both sides the same number is the same thing as doing cross multiplication, right? So does anybody understand? Does everybody get what's going on up there, right? The only difference. Thank you. At least you're being honest when you go, yeah. But don't worry, we'll talk about this again. But the only difference now, since you have a common ion, is that instead of just having x there, so it becomes like x squared, you have an extra number there now, right? That's the big difference. Okay. So again, the same thing can happen. The same thing can happen with the base too, right? So here we have an example of ammonia being added to water, which gives us the ammonium ion and hydroxide, right? And when you add more hydroxides, right? Oh, sorry, not hydroxides. Add more ammoniums. If you add more ammoniums, it makes it so that the hydroxide concentration goes down, right? Because the equilibrium shifts to the left towards the reactants again. So the same thing happens with bases. And you can still do the problem the exact same way, right? Instead, when you're working with bases, what do you use instead of Ka? Yes, Kb, exactly. See, look at her. She's paying attention, sort of. I like how you look around like, am I paying attention? As long as Dr. No thinks I'm paying attention, that's all that matters. Right. So, this is your next question. This is your next. See, this is how I keep you. Yeah, because I knew you guys would be doing this today, so I'm trying to keep you involved. Huh? It's okay. Weird. Really? That's okay though. But yes, there's. I knew this is what most of you would be doing. That's why I added so many questions to keep you involved. Yeah, no problem. All right, which of the following is true about the weak acids, about weak bases, and the common ion effect? The common ion effect applies to weak bases the same way. That seems reasonable. The solution contains a weak the solution contains a weak base and the salt of a conjugate acid. Sounds reasonable too. And then the base won't dissociate as as much as if it were alone. Everybody's answered. Good, good, good. See, I'm so proud. Maybe we should do this all the time. Have you writing stuff while I'm teaching, right? Imagine that, taking notes, maybe. That's crazy. No, I'm kidding. The answer is, in fact, D. All those are true. All those are true. Um, the all those are true, and they do apply to weak bases the exact same way. This time, it's going to be a weak base and the conjugate salt of the salt of a conjugate acid. This time, because it's not an acid, it's going to be the conjugate acid. And then, remember, in the one that was about weak acids, it was like will be more, right? But this one is will be less, so that's correct. And so all of these are true. Okay. let's go ahead and get started talking about how to do this lab real quick. Or actually, let's do some problems first, okay? And then it'll make the lab a lot easier for you. So everybody go to your lab worksheet on the practice problems page, right? If you don't have it, the worksheet with you, just look at it on your computer screens, okay? And these practice problems actually, like I said, are going to be what you're going to have on your exam, right? And so not these specific practice problems, but there'll be a lot like this. And I just want to make sure everybody knows how to do this first, okay? So when we're doing a volumetric titration, one of the things that you have to do is, and I think Ms. Dickens, since I wasn't here for the spring semester, said that you all, when you were in Gen Chem 1, did a titration already before in Gen Chem 1, right? You didn't even do it on like LabFlow or something? That's okay. We'll go through it all today. So the first thing you have to do, right, when you're doing a titration is you have to make what we call a primary standard. And the reason why we have to do that is because if you don't remember, right, when you're titrating an acid, right, you're trying to figure out what the acid's concentration is, okay? But the problem is that what you're doing is that you're going to do a neutralization reaction, and whenever you add in a neutralization agent to an acid that's normally a base, like sodium hydroxide, right, you have to know the exact concentration of the sodium hydroxide before you can actually get the exact concentration of the acid. But the problem with it is that sodium hydroxide is this thing that we call hygroscopic, right? Or hydrophilic if you want to be chemical with it, right? It loves water. So even though when you pull out the sodium hydroxide from the jar and you weigh it out, that's not actually the real weight of the sodium hydroxide. Does that make sense? It's the weight of the sodium hydroxide plus all the water it's absorbing from the air, okay? And so what you have to do is you have to standardize that sodium hydroxide, okay? And you standardize that by weighing out something else that you can weigh out, right? That's not hygroscopic, acts like an acid, right? And acts like an acid and has like a easily weighable mass, right? Molecular weight. So the first question you have here, right? You read the very first question. It says you have a 0.397 gram sample of potassium hydrogen phthalate. That's going to be your primary standard, KHP, right? KHP is your standard. Everybody should just call it KHP because potassium hydrogen phthalate is kind of hard, right? And it has a molar mass of 204.22 grams per mole, and you dissolve it in 50 mils of deionized water, right? And then you titrated it with phenolphthalein, right? Phenolphthalein is going to be the indicator solution, right? It turns pink when things are basic. It stays white or not white, but clear when things are acidic, okay? And you needed 16.22 mils of sodium hydroxide to make the KHP basic, right? So that's a 1-to-1 molar ratio of base to acid to make it turn to the endpoint. Okay. So how do you work this problem? Because it's asking you, it gives you the answer there, right? But it's asking you how you do this, right? What is the molar concentration of the sodium hydroxide solution? So the way you start this out, right? The way you start this out is by first seeing what all you have. Okay. So the first thing you have there is this is number 1, correct? Yeah. So the first thing you have there is the 0.397 grams of KHP. Okay. And you're going to have to do some dimensional analysis here. I hope you guys remember how to do dimensional analysis. There was some of this being done on that discussions question that we did 2 weeks ago. And so for every 1 mole of KHP, we get the molecular weight of KHP, which it's given us here as 204.22 grams per mole. Okay, so that's the first thing you gotta do. Then after that, you've got to figure out what the molar ratio is then, the stoichiometry is then between KHP and sodium hydroxide, right? It's a 1-to-1 molar ratio, so for every mole of KHP, there is 1 mole of sodium hydroxide, right? Okay. And then that should give you the number of moles of sodium hydroxide. And I brought my calculator here. I'm not going to ask anybody to help me with this time because I decided I should stop depending on you guys to have calculators and have one for myself. So all you do is you go through and you multiply this number by this number by this number, and then divide it all by 204.22. So 0.397 times 1, and then divided by 204, and I get this number here, 0.0019 moles of sodium hydroxide, right? And we know that is true because I can cancel out grams of KHP there with grams of KHP here, moles of KHP there with moles of KHP there, and what am I left with? Moles of NaOH. Okay, so that only takes us to the number of moles. What do we do next? Exactly, that's exactly right. Because remember, concentration is the number of moles divided by liters, not milliliters, right? So you can just do that on the fly because you know that 1 liter is equal to 1,000 milliliters, so just move the decimal point 3 times, right? So you can divide all that by 0.01622. And then that should give you a number, okay? And the number that I get when I do that, 19 divided by 0.01622 is I get 0.119, right? Moles of, or molar NaOH. And you can see here, right, that the answer is listed as 0.120. So if I were to just round up because of significant figures, right, this 9 here turns this 1 into a 2. And so your final answer is 1.20, or sorry, 0.120 molar NaOH. You see how, does everybody see how to do that? You're going to be doing the same thing in the lab, okay, with other numbers, okay? Same thing in the lab with other numbers. See, it's good, Mary, that you're here doing this because when you do the lab with Ms. Dickens on Friday, you'll already know how to do these calculations. Any questions on where I got any numbers? That still rounds up to 1.20. Yeah, that's close enough. That is close enough. Mm-hmm. Because there's 1,000 milliliters in how many liters? 1 liter. So that means to convert it, you just move the decimal point over 3 times. Okay? And so that's your answer for that first problem. Okay? Next. So the next question is going to be the next part of the lab, basically, right? Now you have 25 mils of nitric acid solution, right, of unknown concentration, and you put it into a 125 milliliter flask. So this is quintessentially what you're going to be doing in the lab. You'll have a acid. You don't care what the name of the acid is, right? But it's unknown concentration. You put some of it into a flask, right? And here it's 25 mils of it into a flask, right? And then you added 2 drops of phenolphthalein, which is the indicator solution that turns from clear to pink when you get to the end point, which is the point when there's an equal number of moles of acid as there is an equal number of moles of bases, right? That's why it's a neutralization reaction, Okay? And so you use the above sodium hydroxide solution, the one we just figured out, right, as a titrant to titrate the nitric acid. And you got 12.75 mils dispensed into the flask before it turned colors. So what is the concentration of the unknown acid? Okay, so the first thing you need to start out by doing, right, is figuring out how many moles you have of sodium hydroxide that actually move the acid to its endpoint. Okay, so just like what Stephanie just said, you've got to change all your mils to liters. Just do that on the fly again, and so that would be 0.01275 liters of NaOH. Okay, right? So that was 12.75 mils. And I converted it to liters by moving the decimal point 3 places. And then I need to figure out how many moles there was in that volume based on the concentration of sodium hydroxide I had from the previous question. So quite easy. I had 1.19 or 1.2, whatever you want to put there, whatever calculation you got, molar or moles. And if you remember that moles over liters is the unit for molarity, so that's going to be 1.19 mole of NaOH, all divided by 1 liter. So all you have to do there is multiply the 0.119 times the 0.01275, and you should get something like this, something very close to this number, 0.00151. 7 moles of NaOH. Great, great. Okay, that's good. Now you have moles of NaOH, right? So now that you know that 0.00157 moles of NaOH was required to neutralize the unknown acid, you've got to figure out how much of the unknown acid is there, what's the concentration of the unknown acid. So we'll take this number here, go down here since I ran out of room, 0.01517 moles of NaOH. And then we know that the molar ratio between KHP and sodium hydroxide is 1. Just if you were wondering, this is what it looks like. I forgot to write it up here. It's also in your lab too. KHP plus NaOH, right? And then that becomes, I'll just put Kp, sodium Kp actually is what I'm trying to do. Let me write that again. NaKp, there we go, plus water, okay? So notice that in this neutralization reaction, we have 1 mole of KHP to 1 mole of sodium hydroxide, right? So you can write that down there in the dimensional analysis. For every 1 mole of NaOH, you get 1 mole, right, of, oh, sorry, this is the KHP one. So the actual reaction for sodium hydroxide and nitric acid would be this. It would be HNO3 plus NaOH, and that then becomes NaO3 plus H2O. There we go. There's the completed overall equation for that reaction. Forgot to write that out, sorry. And so you see here, for every 1 mole of nitric acid, we have 1 mole of sodium hydroxide. So in my dimensional analysis, I'll go 1 mole of sodium hydroxide equals 1 mole of nitric acid. Writing it wrong. HNO3. There we go. Okay. So again, I can cancel out all these things here. Moles of sodium hydroxide with moles of sodium hydroxide leaves me with moles of nitric acid. And so the number of moles of nitric acid I have is going to be 0.0157 times 1 divided by 1. So that's just the same number again. Moles of, I was about to write out nitric acid, but I'll just write out the formula to keep things consistent. Yes, it is. I apologize. Yes, 0, 0. Thank you. I lost a 0 in there. There we go. Of nitric acid. Okay. So now that you have the number of moles of nitric acid, what do you have to do? It's the same thing you did on the last problem. Divide by the volume of the acid you have, right? But you divide it with it in liters, not in milliliters, right? So the problem said that you had 25 mils, correct? So you divide that by 0.025 liters, okay? And I'll do that real quick. 0.001517 divided by 0.025, and I get about 6, sorry, not 6, but 0.06 molar HNO3. Is that what everybody else got? And I think, what does the answer say? It said it's supposed to be. The answer says it's supposed to be 0.0611. So yes. Everybody understand what's happening? Pretty easy stuff, right? So far? Okay. Huh? Say that again? Yes. Are you getting confused, Mary? What are you confused about? Tell me what you're confused about. What does that mean? Okay, well, let's keep going. We have one more question to do here, which is great because generally you're supposed to do this on your own after the lab, but you're doing it here now. Isn't that great? So you better get 100 on this freaking worksheet. Okay? Yeah, it's a part of the lab. It's a part of the lab. It's a part of the lab with your observations. You know, on your notebook pages, your data that you collect. Okay. So let's answer the next question now. This is a very, this is so funny because this is, they say that this happens, but this has never happened to me before, right? It says a certain chemical industry company, let's say Dow Chemical, for example, right? Or DuPont, right? Or 3M, the people who invented Kevlar, right? Because we spent a lot of time talking about Kevlar today for no good reason, except for it was interesting, right? But anyway, a certain chemical company has a quality control job opening, okay? The job is open for any major with basic knowledge of chemistry, right? So you decided that you're going to apply. In this interview, the HR personnel gives you a sealed folder. How does the HR know anything about chemistry, number one? But HR personnel gives you a sealed folder with a lot to test of your laboratory, with a certain lot to test your laboratory experience, as well as your quantitative and volumetric analysis skills, okay? I will say that they have tested my knowledge before, but not like this in an interview. So the chemical contained in the sample is benzoic acid. And I'm going to tell you right now that the molecular weight for benzoic acid is this. I won't make you calculate it using the periodic table like this guy did, right? So for number 3, benzoic acid is this. 122 112. Not 112. 12212 grams per mole. Okay? Grams per mole. And so it contained benzoic acid and it is known to be a monoprotic acid, meaning it only loses one proton. In order to get the job, you need to determine the sample's purity and see if it is acceptable based on their standards, which is 99.5% purity is what their standard is. Inside the folder, you find the vial labeled BA1, a periodic table, that's generous, a periodic table, and the following data. 1.25 grams of sample required 2 to 20.15 mils of 0.5 molar sodium hydroxide to reach the endpoint. So can this lot be denied if the purity is below 95% or not, right? So what is the first thing you need to do here, right? The first thing you need to do here, just like the last one, right, is you've got to figure out how many moles there is of what? Sodium hydroxide, okay? So it tells you right here that there is a 0.5 molar solution of sodium hydroxide, and it's 20.15 mils of it, right? So you start out by doing you start out by determining the number of moles. So the first thing to do is to, on the fly, convert the 20.15 mils to what? Liters, exactly. So that's 0.0215 liters of NaOH. Draw your fence post, and then you know that the concentration is 0.5 moles of NaOH over 1 liter of NaOH. Okay? So again, you can cancel out the liters of NaOH, you get moles of NaOH, and so the number of moles of NaOH you have here is 0.01075 moles of NaOH. Okay? Cool, cool, cool. So now you know that it's a monoprotic acid, right? So what do you have to do? You got to figure out what the concentration of this monoprotic acid is, this benzoic acid, right? So, okay. So we did it the same way we did the last problem, right? We get our number from over here, the moles of sodium hydroxide. So that's 0.01075 moles of sodium hydroxide. For every 1 mole of sodium hydroxide, we get 1 mole of benzoic acid. I don't know the formula of benzoic acid. Oh, it's up there, but I don't want to write it out, so I just wrote benzoic acid. So moles of sodium hydroxide cancel out, and then it's just the same number again because it's monoprotic. Don't think that it's always going to be like that, though, because sometimes you'll get a diprotic acid. So the molar ratio down here, right, won't be 1 mole of benzoic acid to 1 mole of sodium hydroxide. But if I use the example we did in discussion, which was phosphorus acid, that was diprotic, right? So it would be 1 mole of phosphorus acid divided by 2 moles of sodium hydroxide. Does that make sense? Right? So it's not always going to be 1-to-1, right? Don't depend on it always being 1-to-1. It's just 1-to-1 here. So 175 moles of BA for short, benzoic acid for short. Okay? Good stuff so far? All right, so next thing you got to do, though, is figure out what the purity of the sample is, right? And the way you figure out the purity of the sample is you figure out how many grams you have of benzoic acid, right? From the titration, okay? And so that's quite easy too, because you can just go that number of moles of BA, for every 1 mole of BA, you get the molar weight, molar weight, molecular weight. No, not molecular weight, molecular mass, molecular mass. So that's 100, whoa, that's crazy. What happened there? Can I undo that? Surely there's an undo. Or I'll just erase it. Let you guys catch up. And so the molecular weight then of benzoic acid was 122.12, right? Grams. So here you just multiply the number of moles by the mass, because the moles of BA both cancel out. And then you get, let me see here, 0.01575 multiplied by 122.12, and I get 1.312 grams. Uh-oh, that's weird. That's really weird, right? Because to get the percent purity, right, you're supposed to do the amount that you got in your experiment, right? The grams that you got in your experiment divided by the given number, right? And in the problem, the given number was 1.25, right? So in the experiment, you got 1.312 grams, right, from the experiment, okay? But the label tells you, right, that it's supposed to be 1.25 grams, right? Is that right? Yeah, 1.25 grams. So all you need to do now to figure out purity is to divide these two numbers like that, right? I forgot to say this is given on the label. Divide those two numbers and multiply it by 100 to get a percentage, right? And when you divide it to get 100 to get and multiply it by to get a percentage, I got 105%. Is it possible to get a purity of 105%? No, it's not, right? So this is one of those problems where you got to think about what makes sense, and getting anything over 100% is impossible, right? Does that make sense? Right? So the first question is, what is the purity of the sample? Well, the purity of the sample was 105%, right? And the next question is this purity acceptable? No, not because it doesn't like meet the 99.5% purity thing, but the fact that this number is impossible is why it's not acceptable, right? And then the last question would be, would you repeat the titration experiment? Yes, you would repeat the titration experiment. I can tell you right now, the reason why this went awry is because someone didn't do the volume of sodium hydroxide correct, right? They didn't report the volume of sodium hydroxide that they put into solution correctly, okay? And that's why you got the number that was greater than 100%, right? So this is literally what you'll be doing in lab today, okay? This is what you'll be doing in lab today. So the first step of the lab, before we go in there, right, turn to your procedure page now, right? Turn to your procedure page. And the first thing it says for you to do is standardization of the sodium hydroxide solution, okay? So what you need to do then is calculate the mass of KHP that you need to make a 0.1 molar solution. I'm sorry, not 0.1 molar solution. Yes, a 0.1 molar. What am I saying here? Hold on one second. I lost my train of thought. Oh yeah, sorry. There it is. Okay. Calculate the mass of the. I have it all written all over the place. That's why it's all missed. And then Miss Dickens came in and was like, "Oh, you got to change this number to this and change this number to this," because she's trying to reduce waste. So, calculate the mass of KHP that will require about 15 mils of your 0.01, 0.1 sodium hydroxide solution to reach stoichiometric point, right, or endpoint, right? So, how do you figure this number out? Before you can even go in the lab, you've got to figure this number out. Okay. How do you figure out how much KHP you're going to need to neutralize 0.1 molar solution of NaOH? 15 mils of it. And by the way, when you're making the solution, I want you to use 15 mils. Okay? Don't go it says 15 to 20, but shoot for 15. Okay? Don't make too much because it's just wasteful. Okay? And I'll tell you now that the KHP's molecular weight is 204.22 grams per mole, which I said that before already. Okay. Right there, right after step 2, it says calculate the mass of KHP required to neutralize 15 mils of the 0.1 molar solution of NaOH. How do you do it? How do you calculate it? I'll start you out since nobody's saying anything, right? I know it's been a while since we've done titrations, so I'm going to start you out with this. Okay? Everybody ready? You start with the volume that you need, right? Which is 15 mils. Ah, man. Gotta keep on forgetting to do this. There we go. You need 15 mils of KHP. You need about 15 mils of KHP. Just looking at this now, what do you have to do first? When I say 15 mils of KHP, what do you have to do to that? Exactly, convert it to liters. So easily done. For every 1 liter of KHP, there is 1,000 mils of KHP. Okay, so we just converted it right there. We don't have to do the math just yet. We'll do it all at the end. Okay, and then you need it to be, remember that if you have a molar solution of 0.1 of sodium hydroxide, it's going to take about 0.1 to neutralize it of KHP, right? Does that make sense? Because it's supposed to be the same molar ratio. That's how you do a, not same, it's supposed to be the same number of moles of acid and base to do a neutralization reaction, right? So you can type it, we can write up there 0.10 moles of KHP, right? And you know that this is in liters because it's a molarity over 1 liter of KHP. And then now you can figure out what the mass is because you have the molecular weight I just gave you, right? So for every 1 mole of KHP, there is how many grams per mole of KHP? Yes, exactly, 204.22 grams of KHP. And that will get you to grams of KHP because you cancel out mils with mils, liters with liters, moles with moles, right? The only thing you have left is numbers and what? Grams. Okay? The only thing you have left is grams. Someone do that calculation. Let's see if you got it right. Beautiful. So that's how many grams each of you needs. Okay? 0.06. Oh, sorry, 0.306. So when you get in there, you're going to weigh out 0.306 grams of KHP. Got it? Okay, that's how you figure that part out. Some other things to make note of here. Stephanie actually asked me this question a second ago, but I'll tell everybody else this too. These pirettes are already cleaned, okay? So on step 3, it says prepare a clean burette. It's already clean, okay? It's already clean. So all you have to do is the last part, which is rinse the burette with NaOH 3 times, okay? The NaOH that you're using that we give you, okay? So the part where it says like wash out with tap water and then DI water and all that, you don't have to do that because it's already clean. Just wash it out with, one second. Just wash it out with sodium hydroxide so that you know that the entire thing is covered in sodium hydroxide. Yes, ma'am.
The other thing it does, which I thought was odd, maybe you explain why, is while we are titrating it, it wants us to rinse the inside of the volumetric flask with water. I was like, why would we do that?
Where does it say that? What step is that in?
Step number 5, occasionally rinse the wall of the flask with deionized water in your wash bottle. Continue addition.
Oh, you can do that. And the reason why you can do that is so that you can get all the sodium hydroxide out of the volumetric flask, right? But I think there'll be pipettes in there for you to use too, so you don't have to even use a volumetric flask, right? Because you have to pull out 25 mils, I believe, and You can do that with either a volumetric flask by pouring the solution into the volumetric flask, or by using a pipetter like we did before, a pipette. The thing is, though, right? The reason why that might sound confusing is like, wait a second. If you use some DI water to rinse it out and put it back into your titration stuff, right? Doesn't that change the concentration of the sodium hydroxide? Is that? Oh yeah. Well, see, that's the thing. What happens is that it splashes as you're titrating. The liquid will splash against the side of the flask. It's the DI water is supposed to help you get all that sodium hydroxide back down into the liquid, right? And so the other question is then most people ask, well, doesn't that change the concentration of sodium hydroxide? So it does, but it doesn't matter. You know why it doesn't matter? Because you're talking about the number of moles, not the concentration. Notice how every single thing we did here, we converted straight to moles, right? In every calculation, we converted straight to moles. So the final answer will be a concentration, right? But while you're doing that titration, you're just trying to get the number of moles of acid to be the same number of moles of base. Does that make sense? Right? So it's okay. The only time that it's going to be a problem where you shouldn't do that kind of rinsing is in the burette itself. Because there you actually are measuring out, actual volumes to see how much base or how much acid is going to come through, right? How much base is going to come through the burette. So you don't want to do that with you don't want to wash anything out with the water on the burette. So then the other thing too is that I might as well just go through the steps real quick here. See? So the first thing you're going to do here, right, is you're going to do the standardization of KHP, right? And so let's see here. Yeah, okay, so you'll have a burette. You'll have a burette like this, right? And there's a little stopcock right there, right? And you're gonna open it to let it flow. And you let it flow down to here into this flask, right? And down here is going to be your KHP, okay? And up here will be your sodium hydroxide solution, right? So the first thing I recommend you doing is actually filling up the sodium hydroxide all the way to the top, right? And then last time we got in trouble because we had bubbles, all of us did, myself included, because we have bubbles in the tip of the burette, right? So here's the 0 point right here, right? And I think it's a 50 mil, so maybe the bottom is 50. I can't remember exactly how big these burettes are. But I would fill up your sodium hydroxide all the way to up here maybe, right? Above the 0 line. And that way what you can do, right, is let the liquid flow out into like waste, right? Until you get to the 0 point. And that way you'll get the bubbles out of your pipette tip, or I mean your burette tip too. Does that make sense? Right?
So when we rinse it with the sodium hydroxide solution, because you said we should do that first.
Yeah, for the burette.
Or where are we dumping that?
Waste.
Into waste.
Yes. Yeah, waste.
You said to do that 3 times.
Yeah, discard each rinse in waste. Yeah. Okay. So, and the thing about that too is that when you do that too, you'll have some sodium hydroxide from the rinse in there. So pouring your actual sodium hydroxide you're using to above 0 and then letting it come down to 0, you have to let it stop at 0. Okay. And then you let it go down to 0. And then this excess right here will come out of the bottom tip. We'll remove both the rinse stuff and we'll remove air bubbles. Okay. All right. So after you do that, right, you have what is it called, phenolphthalein in there. You already have the indicator in there, right? And then you just let it drip, 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 drip. Okay. And so what's going to happen is that there's going to be some volume that is required, right? Say, I'm just making it up right now. I don't know what it is. Let's say at 15 mils, right? The liquid was here, like that, and it came down to 15 mils. Okay. Does that make sense so far? And so it took 15 mils for you to neutralize the KHP. Okay? So this right here is the volume, right? That's called the titrant volume. Okay? And your initial volume is this one. Oopsies. Is that one. And this is your final volume. Okay? That's your final volume. The reason why that's important is because when you get into the lab, there's tables in there, right, that ask you, and here we go, right? There's tables in there that ask you, right, what is the burette reading for the initial, right? What is the burette reading for the final? That's what you're trying to do, okay? And then once you get that, you can use that volume and throw it into the dimensional analysis problem that we just did a second ago to figure out the actual concentration of the sodium hydroxide, right? Does that make sense? Because we did that on the practice problem. On number 1 of the practice problem, I believe. Yes. See, number 1 of the practice problem. We had the KHP grams, and we went to the sodium hydroxide molarity. Remember? Right? So all you have to do is take the numbers you got from that what we just did there, that part right there, and do it exactly the same as you would do this, but just plug in the numbers from your burette. Make sense? Okay? And that will give you this right here. This is part 1, and this gives you the standardized molarity of NaOH. Okay? Make sense? Because you need that. Because then, now that you have the standardized molarity of NaOH, or sodium hydroxide, you're going to do this thing again. But this time, instead of having KHP in the bottom, right, you're going to have the unknown acid. And then in this lab, we're calling the unknown acid H2A. Okay? We're calling it H2A, right? So basically means that this is a diprotic acid, right? And the A is the conjugate base. Okay? So you should still have about 15 mils left of your stuff up here, right? You do not have to drain out your sodium hydroxide from the burette and start over again. Okay? Just keep on using the sodium hydroxide that's in your burette. So let's say it takes, it goes down to like maybe 35 mils this time. Okay? So again, you can do the calculation, the change in volume, right? This is your initial volume. And this is your final volume. Okay? So it's always final minus initial, right? So in this case, the final the change here in volume, or the volume that you used, was 20 mils, right? And then you use that number where? In the second problem we had right here, right? Instead of using numbers in the problem, just set up the exact same way as in number 2, but with your numbers. Okay? Does that make sense? Don't worry, I'll be in there to help you if you need it. So that's basically what you're doing today. Okay? The thing that's important is that everybody, myself included, wants to just open up that stopcock and let it just flow, right? But you can't do that, right? You've got to let it go like drop by drop, so that when it turns pink, you stop it immediately, right? Because if you don't let it turn pink, if you don't let it stop immediately, then you're going to have that problem that guy did with the number 3 problem, right? You'll have that problem where you didn't get the right volume because you let it go too far. Okay? Okay, a couple more things to note about the procedure. In Part B, you'll be using a pipette instead of a volumetric flask, which I just said that a second ago. They should already be out there for you. Everybody's doing this on their own. They have their own stuff, okay? And then you'll get a 250 milliliter flask from your drawer. That's what you'll use the entire time, okay? 250 mil, 250 mil. Oh, and then on number C, Part C, it says 1 to 1.5 grams. Use 1 gram for number 1. Again, we're trying to not be wasteful, I guess. We might be out of funds or something. We don't want you to be wasteful. Yeah, that was, yes, instead of using 20 mils, use 15 mils. Yes. That was on number 2. Number 2 in Part A. It says calculate the calculate the mass of KHP required for about 15 to 20 mils. Just make it 15 mils. So we're not wasting stuff.
1 gram, not 1.5 grams.
Right. All right. I literally went through with you every single thing that happens in this lab on the board. I showed you every single calculation you need to do this lab. Okay? So let's go in there and get this done efficiently as possible. Okay? Thank you.